Hello everyone, welcome back to Quantitative Analysis with me, Ferry Afrinaldi. On this video, we will learn how to do a linear programming formulation for a real-life problem. So basically what we're gonna do now is we have a description of a problem, and then based on the description of the problem, we will develop the mathematical formulation of the problem. And since our topic is regarding a linear programming, so the mathematical formulation that we will develop will be the linear programming formulation of the problem. Okay, so we will start from a very simple example, and I think I presented to you this example previously. It is the parking lot problem, and let's visit that problem again here in this video, and we will develop a linear programming formulation for the problem, and we're gonna see if we can solve the problem using the technique that we learned before, which is the graphical technique. If we can do that, then we will solve the problem by using the graphical technique. Okay, this is the problem. So we have a 600 meter square parking lot, and we can use that parking lot to park 58 cars and buses. So the number of cars and buses that we can park combined in that parking lot are 58. And then each car needs a 6 meter square space, and each bus requires a 24 meter square space. And then a car needs to pay 2,000 rupiah, and a bus needs to pay 3,000 rupiah. Now, if the parking lot is full, what is the maximum value of payment the parking lot management can get? Okay, so the thing that we're gonna do, we're gonna translate this problem into a linear programming statement. Okay, when we want to formulate a problem into a linear programming a statement or model, or to any types of mathematical model, the first thing that we need to do is to state the what we call as the decision variable. Okay, so we need to define the decision variables of the problem. Now, from this problem, it is very easy to see that we're gonna have two decision variables. Number one, we call it as x1, and x1 means the number of cars to be parked. Okay, so x1 can be 0, and x1 can be 1, 2, 3, 4, 5, and till 58, right? So it should be in unit. So no car, 1 unit of car, 2 units of car, 3 units of car, and so on and so forth. And the x2, that will be the number of buses to be parked, and that should also be in units. Okay, that's our decision variables. And when we solve the problem, we need to find the value of x1 and x2. We are done with decision variable. And the second thing that we need to decide is the objective function. Okay, so objective function. So see that, so when car park, when a bus park, they need to pay. So we're gonna get income from a car and a bus that parks in the parking lot. So since we get money, so we want to have the amount of money that we get as much as possible. So it should be a maximization problem. Okay. Now, so we know that it is a maximization problem, but still we need to make the mathematical statement of the objective function. Okay, so we are sure that it is a max problem, so put max. Now, what function that we need to maximize? See, a car need to pay 2,000 rupiah and a bus need to pay 3,000 rupiah to park. So if there are x1 cars parked in that parking lot, so we're gonna get money 2,000 times x1. If there are x2 cars parked in that parking lot, so we're gonna get 3,000 times if there are x2 buses parked in that parking lot, then we're gonna get 3,000 times x2 from the buses. So when the value of x1 is 2, then we're gonna get 2,000 times 2, which is 4,000. When the value of x2 equals 3, then we're gonna get 3,000 times 3 from the buses. So that's gonna be 9,000. So it is very easy. So our objective function will be z. So z will indicate or will label the value of the objective function. So 2,000 x1 plus 3,000 x2. That's the objective function to the problem. Now, after we get the objective function, the next thing that we need to have is the constraint. The constraint to the problem. Okay. The first constraint, it is very easy. It is the number of cars and buses combined that we can have in the parking lot. So the first constraint will be number of cars and buses combined that we can have in the parking lot. So we cannot have 59 cars and buses combined. We cannot have 60. We cannot have 61 cars and buses combined. Okay, but we can have 58, 57, 56, 1, 2, 3, 4, even 0 cars and buses in the parking lot. So this means, so the total numbers of cars and buses combined, that means x1 plus x2, we cannot have more than 58. The maximum number of cars and buses combined that we can have is 58. So should be less than or equal to 58. Okay, the first constraint. And the second constraint will be the space. So the total amount of space that we have is 600 meters square. Okay, and a car consumes 6 meters square and a bus consumes 24 meters square. So our number 2 constraint will be the space available. Okay, so see that if we have two cars, then it will consume 12 meters square. So 12 means 2 times 6, right? So if we have x1 cars, so it will consume 6 times x1. So 6 x1 plus a bus require 24 meter square space. So if we have x2 buses, so the amount of space that the buses consume will be 24 times x2, so 24 x2. And remember, we only have 600 meters square of space, so we don't have more. In the meantime, for now, for this problem, it is just 600 meters square that we have. So the sign over here will be the same as the first constraint, which is less than or equal to 600. Okay. Now the last thing that we need to have is the statement for the x1 and x2. Remember, it is the number of cars and buses. So we can have 0 car, we can have 0 bus, we can have 1 car and 1 bus, we can have 2 car and 2 bus, we can have 3 car or 10 bus, 3 cars or 10 buses, but we cannot have minus 1 car, minus 2 bus, or we cannot have 2.5 car, we cannot have 3.6 buses. So x1 and x2 cannot be positive, cannot be negative, but they can be 0. So they must be bigger than or equal to 0. But remember, you cannot have decimals value for you cannot have decimal for the value of x1 and x2. You cannot have x1 equal 3.5, 4.7. No, we cannot have that. So x1 and x2 must be 0 or positive, and they must be integer. Okay. So I think this is it, the linear programming formulation for the problem. So if I summarize all the function that we have, so our objective function is max z equal 2000 x1 plus 3000 x2. Okay, and remember, for the constraint you need to put subject to, but for the subject to I will just put st. So st stands for subject to. So our first constraint is the x1 plus x2 less than or equal 58, and then the next one is the 6x1 plus 24x2 less than or equal to 600, and then the non-negative constraint and the integer constraint x1 comma x2 bigger than or equal 0, and they must be integer. Okay, so this is the linear programming formulation for this problem. Okay, so since we only have two variables, we only have two decision variables here, they are x1 and x2, so we can solve this problem. We can solve it using a graphical technique. Okay, so the graphical technique, it fits for a linear programming problem that has only two decision variables. Okay, so we have x1 and x2, they are the only two that we have, so we can solve this parking lot problem using the graphical technique. Now let's do that. Okay, now So I need to have x2 and x1 space. Okay, now see the first constraint, x1 plus x2 less than or equal 58. So in order to draw a line in this space, in the x1 and x2 space, we just ignore the inequality. We just gonna put the equality sign. So we're gonna just put x1 plus x2 equal 58. So we do this in order to draw a line. So now set x2 equals 0. So when x2 equals 0, then we're gonna have x1 equal 58. Okay. Okay. So we have 58. And then when we set x1 equals 0, then x2 will be 58. Okay, so it is about around here, 58. Okay, now we have 2 points now. Then we can draw a line connecting the 2 point. Okay, it should be a straight line. Okay, just assume that it is a straight line. But remember, in the original problem, the sign is less than or equal to. Okay, so we need to test a point in order to decide the region for the first constraint. So the easiest way is to test the origin over here, the 0, 0 point. So here 0, 0 means x1 equals 0 and x2 equals 0. So 0 plus 0, it is 0. Is 0 less than or equal 58? And the answer is yes. So that means this is the area for the first constraint. Okay, so the area is going to the direction of 0, 0. Now let's plot the line for the second constraint. So here is the second constraint, 6x1 plus 24x2 equals 600. Okay, so when x2 equals 0, so we're gonna have 6x1 equals 600. So that means x1 equal 100. Okay, so if this one is 58, so around here that will be 100. Okay, now when x1 equals 0, then x2 will be, when x1 equals 0, then x2 will be 600 over 24, and that is 25. Okay, so we have x2 equal 25, so it is 25. Let's say that it is around there. So we have 25 over here. Now we have 2 points, and we can connect the 2 points, and we're gonna have a line. Okay, oh, it is something like that. Okay, now the same thing that we need to do, we need to test the origin. So 6 times 0 is 0, plus 24 times 0 is 0, so 0 plus 0 is 0. So 0 less than or equal 600, and the answer is yes, and that is a correct statement. So the area going to the direction of 0, 0. Okay, now the last thing that we need to plot is the area for x1 bigger than or equal 0. So from this point till, I mean, if you go to the right, so that's the area of x1 bigger than or equal 0. So we go to the right, so that's the area of x1 positive, and the area of x2 positive, it is starting from 0, 0, and you go up. So sorry. So this is the area for x2 bigger than or equal 0. So from the plot, it is very easy to see that this is the feasible region, right? This is the feasible region. Okay, so this is not the feasible region, because if we pick this one as the feasible region, so it will not satisfy this constraint. If you pick this as the feasible region, so it will not satisfy the second constraint. Okay, but if you pick this area as your feasible region, so it will satisfy all the constraints. So we have 4 points at the corner of the feasible region: 0, 0 point, 58, 0 point, 0, 25, and this point. But we do not know yet the intersection point that we have over there. So we can find the point by using our high school or junior high school mathematics, and the technique that I'm gonna use is the elimination technique. Okay, so it is the line of the two constraints. So the thing that I'm gonna do is to, I think I need more space over here. Okay, so the first constraint, x1 plus x2, we just put the equal sign 58, and the second constraint is so we have x1 plus x2 equal 58. That's the first constraint, and the second constraint that we have is 6x1 plus 24x2 equals 600. Okay, so I think I need to do this a little bit. Okay, now it is good. Now I think I'm gonna eliminate x1. So I'm gonna eliminate x1. So I multiply the first constraint by 6, and I multiply the second constraint by 1. Okay, so now we're gonna have 6x1 plus x2 equal 6 times 58, that's 348, and then we're gonna have the second constraint times by 1, and so it will not change. So we're gonna have 6x1 plus 24x2 equals 600. Okay, so I think I need to move this a little bit. Okay, and then I put the minus sign here because I'm gonna eliminate x1. So sorry, I think I missed something. So I missed number 6 over here. So 6x1, 6x1, they are gone. 6x2 minus 24x2, then we're gonna have minus 18x2, and 348 minus 600, and that will be 252. Okay, and therefore x2 is minus 252 divided by minus 18, then we're gonna have x2 equal 14. So when x2 equal 14, okay, we know that x1 plus x2 equal 58. So x1 plus x2 14 equals 58. So this means x1 equal 58 minus 14, and that equals 44. So the intersection point over here is x1 44 comma x2 14. Okay, so we have all the points in the we have all the corner points in the feasible region, and the last thing that we need to do is to test each point and find the solution. Okay, now we test the first point. I think I need more space. Okay, this is the objective function. I think I'm gonna need the objective function. Okay, I'm just gonna put it here so I will always see it. Okay. Okay, we test the first point, the origin 0, 0. Okay, with 0, 0, z will be 2000 times 0 plus 3000 times 0, and that means 0. So the origin means we are doing nothing, right? There is no car, there is no bus, so we don't get any money. And the second point is 58, 0. So this is it, 58, 0. So we have 2000 times 58 plus 3000 times 0. So the second points means we only park cars, there is no buses. So we're gonna have 116,000. Okay, and then this point, the intersection point, we have a combination of cars and buses. So the value of z will be 2000 times 44 plus 3000 times 14, and that equals to 130,000. Okay, and the last point is this point, that's 0, 25. So we only park 25 buses. So z will be 2000 times 0 plus 3000 times 25, and that equals to 75,000. Okay, I think I do not need space over there. So see, remember we have a max problem, so we need to find the highest value of z. Okay, this is it. So this is the highest value of z. So the solution to the problem, is x star with, so the x star consists of x1 star comma x2 star. So star indicates optimal solution, and so x1 star equal 44 and x2 star equal 14, and the value of the z star equal 130,000. So this is the what we call as the optimal solution. Okay, and this is it. So for this problem, the highest amount of money that we can get is 130,000, and in order to get that, we need to park 44 cars and 14 buses. Okay, so this is a very simple LP formulation model, and it is also very easy to get the solution to the problems. Now I think I'm gonna give you uh, another example of how to develop an LP formulation. Let me see what I have over here. Oh, okay, let's do this problem. Okay, so there is a company, it is an electronics company. Okay, and the name of that company is Bonner Electronics, and this company is planning for the next week's shipment from its 3 manufacturing plants to its 4 distribution warehouses. So the company has 3 plants. The plants are in Minneapolis, Pittsburgh, and in Tucson, Arizona. Each plant has a potential capacity expressed in cartons of product. So this is the capacity of the plant in Minneapolis, 9,000 units, in Pittsburgh 12,000 units, and in the last plant it is 13,000 units. And then each warehouse has a week's requirement that must be met. So the warehouses are in Atlanta, Boston, Chicago, and Denver. So the requirement for the warehouse in Atlanta is 7,500 units. In Boston it is 8,500 units, and this is for Chicago 9,500 units, and in Denver they need 8,000 units. Okay, there are 12 possible shipment routes, and for each route the unit shipping cost is given. So this is it. So if we want to transport the product from Minneapolis to Atlanta, this is the cost. So $0.60 per unit. From Pittsburgh to Boston, it is $0.3 per unit. Okay. And what the company want? The company want a distribution plan that will minimize shipping costs. So it wants a shipping schedule that will minimize the total shipping costs. Okay. It is the same as the previous problem. The first thing that we need to do is to get the decision variable. The decision variable. So decision variables. Okay. Now I think it is easier for me if I just copy this table. Okay, I think I just need till this one. Okay, I think I need everything. Just copy everything. Okay. Okay, so I'm gonna erase all the number that we have over here. Okay, I think I'm gonna leave those numbers in the last column and in the last row. So here we have 1, 2, 3 plants, and we have 1, 2, 3, 4 warehouse. So yeah, so plant is the rows and warehouse are the columns. Okay, so now let's label rows or plant as I. So so we label it as plant, and J, that is the label for the column, and the column is the warehouse. Okay, warehouse. Okay, now the decision variable will be the number of product that we gonna ship from plant I to warehouse J. So we have I equal 1, 2, 3, and we have j equal 1, 2, 3, 4. And our decision variable gonna be xij, and that's xij means, okay, the number of products shipped from the ith plant to the jth warehouse. Okay, now if I label Minneapolis is as I equal 1, Pittsburgh as I equal 2, and Tucson as I equal 3, Atlanta will be j equal 1, warehouse in Boston gonna be j equal 2, Chicago j equal 3, and warehouse in Denver will be j equal 4. So in total, I'm gonna have 12 decision variable. I'm gonna have 12 xij. So here I'm gonna have x11. That means the number of products that I'm gonna send from Minneapolis to Atlanta. So this is x12. That's the number of product that I'm gonna send from Minneapolis to Boston. So this is x13, and this is x14. This is x21, x23. Oh no, sorry, that should be x22, x23, and x24. And this one should be x31, x32, x33, and x34. So in total we have 12 decision variables. Okay, so this x34 means the number of products that we're gonna ship from plant number 3, which is the plant in Tucson, and to the warehouse number 4, which is the warehouse in Denver. Okay, that's the decision variables. Now the objective function, I'm just gonna put it over here. Objective function. It is very clear that the company want to minimize the cost of shipping. Okay, so it is a minimization problem. Okay, and we have cost data over here. So if you want to ship from Minneapolis to Atlanta, it will cost you $0.6 per unit. So if you just send 1 unit from Minneapolis to Atlanta, it will cost you 0.6. If you send 2 units from Minneapolis to Atlanta, that will gonna cost you 2 times 0.6. Okay, so it is very easy to get the objective function. It will be minimize z equal 0.6 x11, sorry, x11, because x11 will be the number of product that we're gonna send from Minneapolis to Atlanta, and then plus 0.56 x12. This is from Minneapolis to Boston, and this is the decision variable for Minneapolis to Boston, and plus 0.22 x13, and dot means, so on and so forth till the end, which is 0.42 x34. Okay, so this objective function statement should be a longer statement, but I'm just gonna make it short by using dot. Okay, that's the objective function. Now the constraint. Okay, constraint. The first constraint will be the capacity of the plant. Okay, So we cannot send from Minneapolis more than 9,000 units. We cannot send from Pittsburgh more than 12,000 units. And we cannot send from Tucson more than 13,000 units. So what is the total number of products sent from Minneapolis? So that will be X11 plus X12 plus X14. That's the X13 and plus X14. That is the total number of product that we send from Minneapolis, and this total cannot be more than 9,000, so it should be less than or equal to 9,000. Okay, and the same thing with Pittsburgh. So we're gonna have X21 plus X22 plus X23 plus X24, and that should be less than or equal 12,000. And for the last plan, so we're gonna have X31 plus X32 plus X33 plus X34, and that must be less than or equal to 13,000. That's the first constraint. And the second constraint that we have is the requirement or the demand from the warehouse. So the requirement from warehouse. Okay. So the warehouse in Atlanta, it requires 7,500 units of product. So the total number of product received by our warehouse in Atlanta, it is X11 plus X21 plus X31. So it is, we are just following this column. For the capacity of the plan, we just following the row. Okay, so we're gonna have X11 plus X21 plus X31, and we must meet the requirement, so that is why the sign should be equal to 7,500. That's for Atlanta. Now for Boston, X12 plus X22 plus X32 must be equal to 8,500. And then for Chicago, so X13 plus X23 plus X33 equal to 9,500. And then the last one for Denver, then we're gonna have X14 plus X24 plus X34 equal 8,000. Okay. Okay, and now the last constraint that we're gonna have is the non-negative constraint, because non-negative constraint, because we cannot have -1 product, -2 product, -3 product, -0.5 products. We can only have 0 product or 1 product or 2 product or 3 product. So we're gonna put X11, X12 dot until the last one, which is X34, must be 0 or positive. Okay, since it is an electronic products, so I'm not sure if we need to put an integer here, but let's assume that this is an the electronic, we cannot divide the electronic products, so it should be 1 radio, 2 radio, 3 radio, maybe if it is a radio, or if it is a computer, then we cannot have 0.5 computers, so the decision variable must be integers also. Okay. Okay, and this is it, the linear programming formulation for this company problem. Okay, think I'm gonna summarize it for this problem. So this is the objective function. Okay, I'm gonna put it over here. This is the objective function, and then we're gonna have constraint. So st subject to this is the first constraint, the capacity. I'm gonna put it over here. Okay, and the second constraint is the demand or the requirement from the warehouse, and the last one is the non-negative constraint. Okay, so this is it, the linear programming formulation for that electronic company. And see that we have in total 3 by 4 decision variables. So in total we have 12 decision variables. So it is impossible to solve this problem using a graphical technique. So we're gonna need a special technique to solve this kind of problem. I think that is it, and thank you.